I'm honored to keep the presentation on behalf of Sebastian and Thiem, and of course I know the topic because we have worked together, so I didn't have to learn everything from the beginning. But this is part of the Sebastian's PhD study. He has developed a holistic energy system design method, and I will go through what he has done, and also VTT, Sweco, and Savon Voima has been involved in this. Basically, in Finland, we have give supportive information about the initial data about the costs and CO2 factors and these things. So why there is need such a energy system design method is that we want to when designing a district level energy system, there are many possibilities how to do it, and of course we want to make sure that the end results, what will be built at the end of the day, is kind of a cost efficient. The costs are not, the investment costs are reasonable, and operating cost also. And the other thing is, of course, the emissions. So it needs to be, the carbon footprint needs to be as low as possible. So for those reasons, there was development during this project about creating this energy system design method. And basically, this slide illustrates what it is. It is an optimization algorithm at the end of the day. Yeah. So this is the core. This is a mathematical optimization which will do all the work, but it requires initial data. So there needs to be all the technology pre-selections, all available energy production systems, and the parameters and technology cost models also. And then addition to this, it will need this as an initial data. So this doesn't simulate or optimize the use of the energy. It will optimize the production side. And as a result, it will give a selection of technology, optimal capacities, optimal operational schedules, and economical analysis. So this ESD, energy system design method, and it has been developed by Siemens in this project. And once it was developed, we wanted to test it, of course, also. And we used this case Suonenjoki as a test case because there was available initial data which we can use. It was quite a big task to collect all necessary data, and of course the hourly based consumption data for heating and electricity was not available for all the buildings, but then we used a VTT APROS simulation tool to gap the holes from the initial data. It was not the whole Suonenjoki, it was only the center of the Suonenjoki. So the main production facility is somewhere here outside of the picture, and then we have a peak support facilities here. So the reference case was modeled so that it is as close as possible for real case existing at the moment in Suonenjoki. Here is some initial data that we need to dig out. So this was really big task to try to find all the profiles and such things. And also all these other things needs to be adjusted so that the model is somehow reflecting the real situation in what it is at the moment. And there is also, in this model, it includes also opinion for a possibility to residents, the single buildings, to make on-site generation. So that has been accepted in this mathematical model, and it is included in the optimization. So this method was created, developed, and then Suonenjoki was the case to test it. And the first test was to optimize the cost optimal solution. And for those who are not familiar with optimization, it is kind of you have a lot of different combinations, more than you can calculate hand by hand, like in decent time. So the optimized algorithms will computize that, and it searches the optimal solution. It doesn't calculate all the possibilities. It can identify, based on the calculated cases, which direction is the optimal solution. And the first optimization was looking like this. So the only rule in optimization point of view was set that we want to cost optimal solution. And this is the reference case. So this reflects the situation at the moment in Suonenjoki. And what has changed here is that at the moment there is no combined heat and power, and that was installed. And then the optimization showed also that there should be installed hot water storages. And here are the costs. So based on the calculations, the optimization, the more than 25% of the total costs could be saved. But then there comes the problem that if we are thinking about the carbon footprint, this is not actually a very good solution. It's a cost optimal solution, but it's not optimal when you're thinking about carbon footprint. So then you have to actually optimize more than one parameter, not only costs. So the next thing what was done was doing a multi-objective energy system design, aiming for both low costs and low carbon footprint necessary. And the first results was looking like this. And then we end up with discussions that we have had in Finland, at least for the past 6 months or so, is wood carbon neutral? And in this optimization, the parameters were set so that wood is carbon neutral. We are engineers, we are not politics, so we just put numbers there, and then the optimization looked like that. So this is not very interesting results. We think that it's just showing that here you are firing peat, and when you start to optimize, you replace peat by wood. So that's it. If we are assuming that wood is carbon neutral, then you just change peat to the wood. And of course this calculation doesn't take consideration that should we really use our wood for creating hot water, and do we have enough, and how much we can use it. But this is how you can drop the carbon footprint to 0. This is the reference case here, which represent the situation at the moment from the site. But then we did also another case, which we think was a little bit more interesting. So we assume that food is not carbon neutral. And then we start to get something, I would say, nice results. So what happens here is that this is our cost optimized solution, but it has a high carbon footprint. And this is our reference case. And once we start to change peat to the wood here, this moves in this direction, and then at the same time you read this going that way. So what you can see here is that first you will change the peat to the wood, and then you start to use more electricity actually. And we have a bigger slide here with this total. Here is the production mix, how it will actually change when the optimization goes forward. So what happens is, first we have this cost optimal scenario with the quite high carbon footprint. Then we replace peat by wood, we can see here. And this is our wood peat combined heat and power unit. And then if we want to reduce the carbon footprint even more, after this limit we will reduce the use of CHP and increase the use of electricity. And after that we will start to implement also heat pump technology, water-based heat pump technology. And then at the end here comes renewables, in particular photovoltaics. And the final one here, this is the same slide, but it has been scaled because the price will start to go really high. And I think the most important thing here, or interesting thing here, is that normally, for example, cities, they make strategies or how to reduce carbon, or how much they want to reduce carbon footprint. So let's, for year 2000 and something, 20%, and then 2000 and something, after that it's 50%. But here is important, notice that if you are somewhere here and you invest CHP, so your first step is somewhere here. But then your next step is somewhere here. First you invest CHP, but when you want to reach the next step, the technology mix is actually different. So the important message is here to see the whole journey here. And maybe it's not necessarily good to invest in this example in CHP if your goal is actually somewhere here. So to see kind of the whole journey, that's important thing here. And of course this is example calculation, and the method was developed, and then we used the case Suonenjoki. So the more this varies from city to city and case to case. But this is a results where we end up. Yeah, this is the final slide. Basically, I will just open all these right away. So the question is wood carbon neutral or not? That's interesting. Some other people will decide on that one, but of course all these decisions will have an effect of how we build our future energy production systems and so on. But in this case, the story went so that first we replace peat by wood, then we take the utilization of power grid and decrease use of CHP, and then we implement heat pumps and hot water storages, and then finally install renewable photovoltaics and maybe some batteries. But those technology needs to be developed more efficient and also more cost efficient before it's money-wise, I would say. And yeah, that's for my presentation. So thank you very much.
Thank you, Kari. So we are going to the more detailed and more complicated world of modeling, at least for my eyes. Questions, comments for Kari?
Thank you. So just a comment that when you decide not to invest in CHP in your own town and go to trust the grid for the power,
Yeah.
then you lose the possibility to affect the energy sources.
Yeah.
Just a thought.
Yeah, that's
For
true.
the cities.
Of course, of course.
Here's another question.
Well, actually, not a question, more or less comment. My name is Jouni Kivirinen from energy company Helen. You were this comment which came from the lady. It's in this model when you change from CHP to utilization for this power grid. Is there some senses of outsourcing the emissions to some neighbors?
Yeah, I guess there might be. Yeah, of course there
And
is.
that's I know that was, but this is a thing which we have to always take into consideration. If I do one thing, what happens to my neighbor? I think we should make a holistic approach when we look at the emissions. Since when I am decreasing my emission, most likely I will increase some of your emissions.
This was very important point. Thank you so much, and thank you, Kari, once more for your presentation.
Okay.